Okay, in this video I'm going to go over pneumatic power. All right, so pneumatic power, or pneumatics, is the use of gas flowing under pressure to transmit power from one location to another. Gas is a pneumatic system, and it behaves like a spring since it's compressible. All right, there's so much space in between gas molecules or gas atoms, mostly they're molecules, and they're bouncing around, and the more heat, the larger the temperature, all right, again, more heat it is, the farther apart it's going to be. So then you can compress that because there's so much room between these molecules. All right, so just like a spring, you can compress gas. All right, so in a pneumatic system, compared to hydraulics, we're going to start with pneumatics. This PowerPoint's all about pneumatics, and then later I'm going to go over hydraulics. But pneumatic system is going to be compressible gas. Hydraulics is going to be like oil or water or some type of a liquid. Right? So the process possesses a quicker, jumpier motion, and they're not as precise. They're generally cleaner. They often operate at pressures around 100 psi. They generally produce less power. All right, and that's just talking about pneumatics. When we get to hydraulics, I'll talk a little bit more about the benefits or, kind of pros and cons of hydraulics, where we talk about pros and cons of pneumatics here. All right, so earlier pneumatics, you might recognize something like this, right, called the bellows. It's the bellow. The tool is used by blacksmiths and smelters for working iron and other metals. You might also see it by somebody's fireplace to try to get enough oxygen to that fire so it'll work. All right, here's another example. All right, Otto von Guericke showed that a vacuum can be created. He used a pump to pull out the air to cause that pressure inside of those, I guess you could say, it says hemispheres, but those half circles, yeah, hemisphere. You can pull out the air, which causes the pressure inside to go down because, air has pressure itself because of the molecules. Well, you pull those molecules out, those air molecules, and you're going to have less pressure. Then he showed here that if you hook up horses and pulled, that you would not be able to pull those apart, right? Showing the basically the presence of that pressure because the atmospheric pressure is keeping it together. Not even those horses was able to pull it apart. Another example here of pneumatics, earlier uses. All right, the first subway was designed by Alfred Beach. It was built in New York City and was completed in 1870. 312 feet long, 8 feet in diameter, and then it closed in 1872. So obviously a pneumatic subway was not really the way to go. It's kind of sad they probably spent longer building it than they actually used it. All right, but properties of gases. All right, gases are affected by 3 variables. Temperature, just like we just talked about. All right, if you heat it up, you have more pressure, because the molecules are going to be moving around faster and they're going to be spreading out, which would also cause you to have more volume, so on and so forth. Gases have no definite volume, and gases are highly compressible. Gases are lighter than liquids. Obviously, that really should say more like density, because gases are going to be less dense than a liquid, simply because what we're talking about, there's so much space in between those molecules compared to a liquid. All right, so let's first start off by talking about pressure. All right, so we talked about that it's temperature, pressure, or volume. We're going to start off by talking about pressure, atmospheric pressure. All right, so air has weight, has all those molecules. They're taking up space. Just because you can't see it doesn't mean it's not there. All right, the molecules are still there. Obviously, we breathe. We need oxygen. So those oxygen molecules must be in the air, even though you can't see it, which causes it to have weight because it has molecules, which would be mass. All right. So air is like a fluid that is several miles deep, right? Because gas a lot of times, or not a lot of times, gas is a fluid. right? So we have, like it says, air is a fluid that is several miles deep. And because of wind, you have less, there's a lot more wind as you get higher in the atmosphere. And also gravitational pull is going to also affect the reason why we don't have as much air the farther up we go. Right? Pressure is a force per area. At sea level on a standard day, all right, air pressure is going to be 14.7 pounds per inch squared, which you'll also see written as PSI. So 14.7 PSI, or also 101.32 kilopascals. In the American system, we use PSIs. In the metric system, they're going to use, well, actually the SI unit is pascals, which is this PA here. But because those are such large numbers, if you think about atmospheric pressure right here, 101.32 kilopascals, if I put this in the actual SI units, like you've learned in science, you're looking at moving that decimal another 3 places to get that converted to pascals. And that's why more than likely you're going to see it more in kilopascals instead. So let's kind of talk about a straw, because that's something you use every day. All right. So air pressure in the straw is less than the outside air pressure. Whenever you put that in, it's kind of worded funny, but you put a straw into your liquid, right? Because of air pressure, a little bit of water is going to go up into the straw, right? Up until it equals out. You're going to have that equilibrium where the atmospheric pressure is going to be pushing down on the water or whatever liquid that you have in there. And so whenever you put in that straw, that atmospheric pressure is going to balance out to where the straw has the same amount or the same level as the beverage. All right. Now, if you take that straw and you suck it in, you are reducing that pressure. You're pulling that pressure. All right. So now the atmospheric pressure is going to be a little greater, and it's going to push it down, and you're basically removing that pressure whenever you suck through the straw. Also, another thing which you might see, I don't know if you've ever tried this, and it works a little better if you have one of those like bigger straws that kind of you get with thicker, I don't know, sometimes Brahm straws are a little bit bigger or whatever. But if you have a liquid in there and you blow across the top of the straw, all right, so you kind of blow across it, and it really works better if you have maybe a fuller liquid, so that way it doesn't have as far to have to travel. But you blow across the top, and that causes the air pressure to reduce because it's got that wind. So now my pressure on the top of the straw is less than the atmospheric pressure pushing down on the liquid. So it's going to cause the liquid to come up into the straw a little bit, and as you're blowing across it, it's going to cause that liquid then to come out and kind of spit out, which of course I probably shouldn't teach you that kind of stuff, but it's kind of fun. So sometimes too, in like a demonstration, you'll see people where they'll take confetti and they'll have one of those, like a big tube that they stick down in it, and then they blow like a leaf blower across the top of that cylinder, and the confetti will come out and blow across the audience. I don't know if you've seen that or not, but it's just reducing the pressure, the atmospheric pressure on top of the straw or the tube, and the atmospheric pressure pushing down on the item, the liquid, or like the confetti in that case, is greater, so it's going to cause it then to blow out of the straw. So again, I don't know if that's something I should be teaching you because I don't want y'all to get in trouble at lunch, but so basically the outside air pressure forces that fluid up the straw. All right. All right, so air pressure decreases as the altitude increases. All right, so Denver Broncos play at the Mile High Stadium. Also, if you like go mountain climbing, a lot of times you've got to kind of get acclimated because it's going to have less oxygen, right? The higher it goes, there's less air pressure. A lot of times on boxes of things, whenever you're trying to figure out how am I going to bake this pasta, you're going to boil it. And it'll say something like, if you're baking this or boiling this at high altitudes, you're going to want to maybe boil it longer or bake it at a different temperature, simply because of that air pressure. All right, that's why we have to pressurize airplanes, because the higher up, the air pressure is going to change, and obviously you need to pressurize those airplanes to make it comfortable for people whenever they're flying. All right, oxygen required above certain altitudes is obviously the biggest reason why you need to pressurize those airplanes. All right, so again, what we just talked about a minute ago, the difference in pressure as you get in those higher altitudes is because mainly the wind. And like I said, gravitational pull of those molecules. But the wind is blowing harder the higher up you get into the atmosphere. All right, so air pressure supports a column of mercury, 29.9 inches, or 760.0 millimeters. So what that means, and I'm sure you've kind of heard about it maybe in some of your science classes when we talk about air pressure. When you take a tube of mercury, now of course this is something we don't really play with anymore, even whenever I was in science. Yes, I'm not really that old. I didn't get to play with it either. But this is what they did, and this was kind of where they really started figuring out air pressure, is you take like a long tube, obviously at least 30 inches tall, you fill it with mercury, and you flip it upside down into a container. It'll start dumping out. Well, while it's dumping out into this container, a vacuum is forming here, because air is not getting back up into the top. So the air pressure eventually is going to be great enough that the mercury is not going to come out anymore, because this air pressure is pushing down on your little bowl, your little pool of mercury. This is a vacuum, so there's no more pressure pushing the liquid mercury out. Right? This is something you may have seen. Like a dog or cat water bowl. Sometimes you'll see these. You fill this completely full. When you flip it upside down, it's going to fill this bowl, right? And also this part with water. Well, this part here is going to form a vacuum. There's no air to push, to have that, pressure to push it out. So the atmospheric pressure is going to keep it into the bottle. And then, of course, as the animal drinks or, it just evaporates, it's going to eventually more is going to come down, simply because it's going to equalize. It's going to get in that equilibrium of the air pressure in the weight of the water or whatever it is. So hopefully that kind of makes sense. But if we talk about standard pressures, right, at sea level, what do we consider a standard pressure is 1 atmosphere, which is also the same thing as 760 torr, which is also 14.7 psi, or 760 millimeters of mercury, or 101.3 kilopascals. Just like everything else we've talked about whenever we talk about work, being like joules or calories, there's always more than one type of unit. Lots of people in the past have done calculations and studies, and they all want their name on it. They all want to name what they've studied. And so you end up with a lot of different units of what has been named. But they're all basically the same thing. Every one of these measurements here is measuring the exact same pressure. So whenever we do a standard temperature and pressure, which I'll talk about in a minute, but standard pressure is this 1 atmosphere and so on and so forth. If I want my unit to end in millimeters of mercury and I give you the first one in atmospheres, then you know how to convert, right, by using dimensional analysis like you've learned before in the class. All right, so these are your standard pressures. All right, so properties of gas again. we're going to look at, like I said, absolute pressure as well. All right, so that here is standard pressure at sea level. Now we're going to talk about absolute pressure. And what we mean by absolute pressure is the pressure you get off of a gauge, all right, is not going to account for atmospheric pressure, right? Because it's in a tank, it's coming from a gauge. So if we want to consider what that would be with atmospheric pressure with it, my absolute pressure is going to be atmospheric pressure plus that gauge pressure. Okay, so the gauge pressure is just kind of what you read off of here. This is a little bit less than 15, and I'm pretty sure it's PSI. And then the absolute pressure is going to be whatever the atmospheric pressure is plus that gauge pressure. Okay. Here. All right, so pressure is measured in pounds per square inch. That's usually what you're going to see, PSI, on most of your stuff in engineering, because here in America we use mostly PSI. That's what most of our gauges are going to measure in. Your standard atmospheric pressure, again, standard atmospheric pressure equals 14.7. That doesn't mean right here in Oklahoma, if I took the not the standard again, let me get rid of standard. If I take the atmospheric pressure right now, it's not necessarily going to be 14.7. That's standard at sea level. And then you always hear about systems coming up, high pressure, low pressures, things like that. So it might be changing a little bit depending on the day. But a lot of times it's easier just to say, let's just go with standard, get that ideal, kind of like whenever you're talking about theoretical, what is my theoretical pressure going to be? Sometimes it's easier just to use that standard atmospheric pressure when we're working problems. All right, if a gauge reads 120.0 psi, what is the absolute pressure? Well, we just take 120 psi plus 14.7 psi, if we're using standard, okay, would be 134.7 psi. All right, so let's also talk about temperatures. And we've already talked a little bit about temperatures in the last, in one of the other units, but absolute temperature, if we look at absolute zero is when all motion has stopped. All right, we have no heat in that system. So absolute zero would be negative 460 degrees Fahrenheit or negative 273 degrees Celsius. Now I know there's some decimals on there, but for our purposes, we're just rounding. All right, which is where a lot of those significant figures come in. Whenever you kind of wonder why we use them, this is why. But so here we've just kind of rounded. But so my absolute temperature is going to be measured in either degrees Rankine or Kelvin. And we have to make sure that we use either degree Rankine or Kelvin when we're working our gas problems, because we have to have it on an absolute scale. And if you want to kind of test this and kind of understand why, is if it's not on an absolute scale, we can't really multiply or divide with it. Because if I say 10 degrees Celsius and I double that, well, that's 20 degrees Celsius. But on an absolute scale, if I say 10 degrees Celsius, so that's 273 plus 10, 383, and I double that, and then say I subtract that 273 again, I am not going to end up with 20 degrees Celsius. It doesn't multiply and divide the same way, right? So an absolute scale can multiply into, yes, I have that much more. I have double the amount of average kinetic energy with an absolute, where if you have a degree Fahrenheit or a degree Celsius, you can't double it and say, I have twice as much heat or average kinetic energy. Okay, so hopefully that kind of makes sense. If not, just remember, always convert it to either Rankine or Kelvin. If you have it in degrees Fahrenheit, change it to Rankine. Use all of them in Rankine. If you have it in degrees Celsius, change it to Kelvin. Now that's to work the problem. Once you've finished working the problem, you need to convert it back to degrees Fahrenheit or degrees Celsius. And the reason why that's important is we talk with degrees Fahrenheit or degrees Celsius. No one's going to say, hey, it's 323 Kelvin outside today. Nobody's going to know what that is. So you always need to convert those temperatures back to degrees Fahrenheit or degrees Celsius, depending on which one it started with. But you have to, again, use absolute scale to do the problems. So your standard temperature, sometimes you'll hear standard temperature and pressure, which is STP. So your standard temperature is either 273 Kelvin or 492 degrees Rankine. And if you'll notice, that's basically the freezing point of water. All right, so if the temperature of the air in a system is 65 degrees Fahrenheit, what's the absolute temperature? We're just going to add 460 to get 525 degrees Rankine. So if I said, hey, it's 525 degree Rankine outside today, nobody's really going to know what I'm talking about. So again, after I finish working with it, I would then subtract 460 to get that degrees Fahrenheit again to express my answer. All right, so we're going to start off with Pascal's law. All right, so pressure exerted by a confined fluid acts undiminished equally in all directions. All right, so pressure is the force per unit area exerted by a fluid against a surface. So this is the equation you're going to use. Pressure equals force over area. That's where we get PSI, pounds per inch squared. All right, if I was in pascals, that is a Newton per meter squared. Okay, Pascal, that's what Pascal equals. So, Pascal's law, example, how much pressure can be produced with a 3-inch diameter cylinder and 50 pounds of force? Okay, so we write down our knowns. Okay, I'm going to find my area, pi r squared. All right, so it's 7.1, so I'm going to plug that in for my area since I had the diameter. And now I'm going to plug in my pressure is going to equal 50 pounds divided by 7.1 inches squared. Okay, and knowing that, in pascals it's Newton per meter squared, more than likely Pascal's law was more with the metric system. But because we're engineering, we're in the United States, that's why we use PSI instead. Okay, so the final is 7.0 pounds per inch squared. So it says the perfect gas laws. We're going to talk about Boyle's law, Charles' law, Gay-Lussac's law, and then we're going to talk a little bit about the fact that you can combine those all into one if you have everything changing instead of one thing staying constant. Okay, so here's Boyle's law. When we increase the pressure, right here, we increase the pressure, my volume's going to go down. Right, so the volume of gas at a constant temperature, notice this is assuming that we have a constant temperature, is going to vary inversely with the pressure. Okay, so this is what the equation looks like. P1 times V1 equals P2 times V2. In this example, we're looking at volumes in inches cubed. Now, volumes can be liter, milliliter, it can be meters cubed, inches cubed, centimeters cubed, so on and so forth. It's always going to be, though, a volume is always going to kind of be the same units. When you're looking in one of those problems, you're trying to solve an equation, and you see something cubed, you know it's volume. Or if you see it as liter, milliliter, or quart, it's a volume. If you see something in grams or slug, it's going to be a mass. That's how you kind of wonder. Whenever you're reading through and you're just kind of trying to pick numbers out, you know what they are based on what unit they are. All right, so here's an example. A cylinder is filled with 40 inches cubed, again, that's a volume, right, because it's inches cubed, of air at a pressure of 60 psi. Psi, I know that's a unit for pressure. The cylinder is compressed to 10 inches cubed. Right, my units are matching. That's great. What is the resulting absolute pressure? All right, so we look at the fact that this is in psi, so my answer is going to be in psi. Okay, so here is my knowns. Okay, I've got to convert first that 60 pounds per inch squared, or psi. I need to convert it into absolute pressure because it does ask for the resulting absolute pressure. Now, if it told me this was absolute pressure and it wanted it in absolute pressure, I wouldn't have to go through this step first. But notice that I've got two different types of pressure and I have absolute pressure. So that's why I've got to do that. So here's my formula, and I'm going to plug it in. Solve for it. Okay, and they're putting it into correct number of significant figures because I have 2 in each of these due to that decimal after it, making those zeros significant. Okay, so Charles' law. Now, as you can tell here in the picture, we're increasing the temperature. We add a fire to it, we increase the temperature, and because I'm increasing the temperature, my volume is going to increase. Notice I'm not doing anything with pressure. Pressure staying the same. So, as it says here, volume of gas increases or decreases as the temperature increases or decreases. So it is directly proportionate. Okay. So here is the equation. Volume 1 over temperature 1 equals volume 2 over temperature 2. And notice too, these temperatures have to be in the absolute temperature, either degree Rankine or Kelvin. Right, so an expandable container is filled with 28 inches cubed of air, notice that's a volume, and is sitting in ice water that is 32 degrees Fahrenheit. The container is removed from the ice water and is heated to 200 degrees Fahrenheit. What's the resulting volume? Right, so let's put in all of our knowns. Notice we're going to have to convert those to Rankine by adding 460. Right, so now we're ready to plug it into our formula. And the best way to do this is to cross multiply. My unknown is this one here, V2. So I'm going to say 28 times 660, and then I'm going to divide it by 492. So you multiply the ones together here, crossing across here, cross multiplying like an X, and then you divide by the ones that have the unknown. So that's why I'm dividing by 492. My first unit here is inches cubed, so my resulting answer is going to be also in inches cubed. Gay-Lussac law. Absolute pressure of a gas increases or decreases as the temperature increases or decreases, provided the amount of gas and the volume are going to remain constant. So I'm not changing the amount of gas that I have in there, and I'm not changing the volume. It's maybe a cylinder, right? You've seen those cylinders like welding companies have with oxygen or whatever in it, helium. Those aren't going to change. And so when those get heated up, the pressure inside is going to also increase. All right. So these are directly proportionate again. Notice temperature again is in absolute. And your pressures also would be in absolute. Okay, so pressure 1 over temperature 1 equals pressure 2 over temperature 2. And so here's an example. A 300-inch cubed sealed air tank is sitting outside. Notice it says sealed air tank, so that means my volume is not going to change. In the morning, the temperature inside the tank is 62 degrees Fahrenheit, and the pressure gauge reads 120 psi's. Notice the pressure gauge, so that means we're going to have to change that to an absolute, right? By afternoon, the temperature inside the tank is expected to be close to 90 degrees Fahrenheit. What will the absolute pressure be at that point? Okay, so here's my knowns. This pressure 1 I'm going to have to convert by adding 14.7. Again, we're assuming a standard pressure not actually taking the atmospheric pressure at that exact time. All right, so convert P to absolute pressure, 134.7 psi's. We've got to convert our Fahrenheit to degree Rankine by adding 460. I'm going to plug those in. And so then my pressure is going to be now in that absolute pressure because the other one was. So it's 140 psi. All right. If the absolute pressure is 141.9 pounds per inch squared, what is the pressure reading at the gauge? Well, again, if you need to go from absolute pressure and then you want to find out what the gauge is, then you would subtract 14.7 psi. Okay. Significant figures is why they changed it to 130. So you can also do this if you don't have anything changing. I'm sorry, you don't have anything staying constant. All right, everything is a possibility of changing. All right, the heat's changing, so the pressure's changing, and it's not a cylinder and a closed system. So in that case, you'd use a combination. All right, the combined gas law is a gas law that combines Charles' law, Boyle's law, and Gay-Lussac. There is no official founder of this law. It is merely an amalgamation, yeah, you can pronounce that on your own, of the three previously discovered laws. So if I have something that says 2.00 liters of a gas is collected at 25 degrees Celsius and 745.0 millimeters of mercury, what's the volume at STP? Remember I said standard temperature and pressure. In this case, I have a standard pressure would be in millimeters of mercury because my given is in millimeters of mercury. That's how I know which one to choose. So I'm going to say 760.0 millimeters of mercury. Volume is what I'm trying to find. All right, start with 2.00 liters. What is the new one? And this would be something like maybe a balloon or something like that doesn't have a consistent volume. And then the temperature is already given to you. We can go ahead and say, standard temperature 273. We have to convert 25 degrees Celsius to Kelvin. All right, and plug them in. Again, cross multiplying. Like I'd said, here's my X. So what I'm going to do to plug it into my calculator is I'm going to say, and go ahead and try this just to make sure you do it correctly. I'm going to say 745.0 times 2.00 times 273. Then I'm going to divide by this part here. And so I'm going to say divide, and if you have one of those graphing calculators, you need to open up a parenthesis and say 298 times 760. Close your parenthesis and then hit enter. Now, if you have a cheap one, like what I use, all right, it's gotten me through all my calculus, though, in college, I would type it in as 745.0 times 2.00 times 273. Then I would hit the divide button, and I'd say divided by 298, and then I'd say divided by 760. And then I'd hit enter, because I don't have the neat little parentheses around mine. So it depends on what kind of calculator you're using. All right, but that's going to give you 1.80 liters. Here's some common pneumatic system components. All right, you've got a receiver tank, transmission lines, compressor. Got to compress the air somehow, right? A cylinder, filter, regulator, drains, directional control valve, pressure relief valve. Okay, so these are just some examples. Now here is an example of something that you've actually seen and probably used. All right, so whenever, look, I guess go through what they are first. We've got the piston rod, the pump handle, the pump tube or cylinder, the pressure gauge, the piston inside here, and then the foot stand, and the fill valve with a locking lever. Right? So if you think about this with pressures, all right, you can feel the energy you are expending while pumping the reservoir up to the right pressure. The work you did compressing the air into the reservoir is now available to the pneumatic system that you have built here or that you're using with the bicycle pump. All right, so each component either stores, controls, or transforms the pressurized air you pumped into that cylinder. Okay, and that's the whole point of these pneumatics. By compressing that air, you have added energy to it to compress the air. Now it has the energy in there because, it cannot be created nor destroyed. It's got that available energy in there now that you have put it in. Okay? So a pneumatic reservoir, here's an example of one. One touch quick connect fitting connects to the three-way valve, which I'll show you in a minute. All right, so energy is stored as compressed air, like we just talked about. Okay, so the reservoir is like a battery. Instead of housing stored chemical energy that can be released as electrical energy, the reservoir stores energy in the form of compressed air. Some of the work done in pumping or pressurizing the reservoir can be converted back into useful work by the pneumatic cylinder or actuator. Right? The capacity of the storage reservoir is a product of the internal pressure times the internal volume. Its stored air capacity is always given in terms of standard pressure. Okay. So here's the three-way valve. Right? Three-way valves are used to activate or pressurize the pneumatic circuit. The valve vents or depressurizes the downstream components each time it is turned off. This is an important safety feature. Right, so every pneumatic circuit should include a three-way venting valve. By depressurizing the downstream components, the working pneumatic components are deactivated and the mechanisms they control cannot be operated accidentally. Okay. Here's the regulator. Right, the regulator controls the air pressure of the pneumatic circuit components downstream of the regulator. The designing machines that work effectively with lower pressures means you will have more effective reservoir capacity. I'm having a hard time pronouncing things, sorry. Right. Another regulator continued. Okay, just some other parts that you might see on a pneumatic system. Okay, here it says be certain to verify the direction of the airflow through the regulator. The incoming air from the three-way valve enters the port marked with an arrow. Right. The solenoid valve. The solenoid valve has three ports: the pressure inlet port 1, the actuator port, and the exhaust port. The solenoid has two modes of operation, on and off. In the de-energized state, the pressure port is closed. The solenoid is specified as a 3/2 normally closed solenoid valve. Be certain to connect the port 1 port to the pressure side whenever you are putting something like this together. Okay. The pneumatic cylinder or linear actuator. Okay, that's another piece that's common that you might see. The pneumatic cylinder or linear actuator transforms the stored energy of compressed air into useful work. The cylinder stroke refers to the difference between the actuator's length at full retraction and full extension. The bore refers to the interior diameter of the cylinder body. Theoretical force of the piston is a product of the pressure times the area of the piston. Right, these are one-touch quick connectors. You'll see those sometimes on pneumatics operating. Pneumatic component connections. Then you would build it, test it, and use it with all of these parts. Hopefully this has given you kind of an introduction to pneumatics so that you understand and know what they are whenever you see them and how they work.